Hello everyone, welcome to the 12th lecture of dynamics. So let's start with a refresh of the main formulas about the kinetics of a rigid bodies or a rigid body. So kinetics of a rigid body, sum up of the equation, okay? Sum up of the most important equations. So let's consider we have three cases. Let's consider. So okay, maybe like this it will work better. So we have the with respect to the center of mass, which is indicated with S. Then the point with zero velocity, and then maybe put some more space here and then here we have a generic point, okay? Generic point. Okay, should be fine. And yeah, center of mass S, you know what it is. Point with a zero velocity, so let's consider a generic point VA, whose velocity VA is equal to 0, but in general, his acceleration is different from 0, okay? In general. And then we have here we consider a generic point, let's call it B, so we have VB is different from 0 and AB is also different from 0, okay? So let's see the basic law of dynamics. So we have m, the mass times the acceleration of the center of mass is equal to sum of all the forces. And this is valid only for the center of mass, so even if I go with a point with zero velocity, we still have m times as is equal to f, because it's not valid with respect to point with zero velocity. It must be done with respect to center of mass. Also here I will write m times as is equal to f, okay? Now let's see the kinetic moment. So ds is equal to ms. Okay, and this is also part of the basic law, like principal law of dynamics. But this is valid for any point. So we have dA is equal to ma, and we can have also with respect to generic point B, dB is equal to mb. Okay. The only thing is that the ds, dA, and dB are not the same in the three cases. Okay, so we have in the case of the center of mass, we have the ds is equal to pi s dot. Okay, and if we have a point with zero velocity, then we have that dA is equal to pi a dot, which is also quite convenient. But in the case of a generic point, we have that dB is equal to pi b dot, sorry, pi b dot, and this should be a b, so pi b dot plus velocity of point b cross product the mass of the rigid body times the velocity of the center of mass. Okay, so this becomes a little bit more complicated. Now, what is pi? So the angular momentum. So we have pi s is equal to theta s times omega. Then if we take with respect to the point of zero velocity, we have that pi a is equal to theta a times omega. Take here is theta s, here is theta a. You know, theta, to compute theta a, you have to first know theta s and then move to point A using the parallel axis theorem. But apart from that, now here we have instead pi b is equal to theta b times omega, and now we have another term here plus r bs cross product m mass times the velocity of point B. Okay, so you see now this also starts to get more complicated if you consider a generic point instead of considering the center of mass or a point with zero velocity. And what about the derivative of P of pi s of the angular momentum, which we need to compute the kinetic moment? So pi s dot is equal to the derivative of this, so is theta s times epsilon, so the angular acceleration, plus omega cross product theta s times omega. Okay, and take care, this guy is pi s, while here the derivative of pi a is something like this, pi a dot. This is a little bit more complicated. Here we obtain theta a times epsilon, so far same as we have here, plus omega cross product theta a times omega. Okay, but here we have an additional term, plus, that I write down here, plus RAS cross product m times a acceleration of point A. Okay, so this term appears because here we could eliminate this term basically, because the difference between point A and point B is that velocity of point A is 0. So if you take this and know velocity of the point you are considering is 0, you eliminate this term. That's why here we don't have this term. Okay, but now when we take the derivative of this, the derivative of the velocity is the acceleration, here the acceleration is not 0. Okay, that's why here it appears again, this term, and that's why in general it's convenient to consider with respect to the center of mass this, and not with respect to a point with 0 velocity. Unless this point has also 0 acceleration, in that case you will eliminate also this term. Okay, but if it's only 0 velocity, then this term is still there. Take care, because this is often forgotten. It can be forgotten. Okay, so yeah, just take care about that. Okay, and then here we have pi b dot is equal to theta b times epsilon plus omega cross product theta b times omega plus rbs cross product m times a b, and this is the same term that we have here, and here we have an additional term which is minus vb cross product m vs. Okay, and yeah, this term we don't have here because the velocity of point A is 0. So if you take this term, put VA here, it will be 0. Okay, so actually from the generic point you can always go to these ones. Okay, because you just assume that instead of a point B you have point S. Okay, so for example here instead of here instead of VB you put VS, you will have that this is parallel to this vector, so this term will be 0. And here if you have instead of B you have S, you have RSS, which is 0. Okay, so this term is also eliminated. And similarly here, if instead of B you have S, it means this will be 0, and then you will have that Vs is parallel to Vs, so this will also be 0, and you will be left with this, where B is substituted with S, which is the same thing that we have here on the left. Okay, so yeah, so that's it. So it's good to know formulas for the center of mass is the one that you should apply in majority of cases. It's good to know also for a generic point, and to find the relationship between the two. Okay, now but we know that what we really need is this equation is the one we need when we write the equation of motion. We apply the first law of dynamics, the main law of dynamics, how do you want to call it, and this will give us here will give us theta s. So basically this pi s dot, because pi s dot is ds, times epsilon plus omega cross product theta s times omega, and this is equal to ms. Okay, so this is the formula that you really need to know. Okay, you really need to know because you will use all the time. And remember that this is pi s. Okay, so this one I put try to highlight this formula. Then let's see what we have in the case of a point with zero velocity. We will have theta a times epsilon plus omega cross product theta a times omega plus RAS cross product. Sorry, this is not really readable. This is an S cross product mass times A, which is this term, and this is equal to MA. Okay, and also this I highlight because this is, again, this is the important equation. If you have a point with zero velocity, this is what you will need to apply. Okay, and now let's go for a generic point. Here we'll have theta b times epsilon plus omega cross product theta b times omega plus plus RBS cross product M times AB, and this is equal to MB. Okay, and now you see I get back one term. I eliminated this term because this term is basically is compensated by this one. Okay, because you see dB is not equal to pi b dot, is equal to pi b dot plus VB cross product MVS, which is the same term we have here, just plus minus, so they eliminate, we can eliminate each other, and we obtain this formula. So you see that the fact that the point has zero velocity practically does not really help us much when we have to write the equation of motion. Just you have to pay attention to one thing, that this here we have this guy theta s times omega is pi s. Here we have theta a times omega. This is also pi a. Okay, you see here, but this is different from pi b. Okay, because pi b is not just this, we have also this term. Okay, so here you have to, if you have, once you have to use this formula with respect to a generic point, take care that this is not pi b. Okay, so this is this I stress that this is not pi b. Okay, and the last formula that I want to remind here is K. So kinetic energy is equal to 1 over 2 times mass times Vs the power of 2 plus 1 over 2 omega transpose times theta s times omega in the case of the center of mass. In the case of a point with zero velocity, and this is simpler than with respect to the center of mass, because it's just 1 over 2 times omega transpose times theta a times omega. And finally, in the case of a generic point, which I personally never used in my life because it's really not a smart choice. I never encountered a case where it was convenient to use a generic point. It's like 1 over 2 VB squared plus 1 over 2 omega transpose theta B omega plus we have this additional term which I also don't even remember usually, so it's mass times VB times omega cross product RBS. Okay, so this was explained I think 2 weeks ago in lecture 10 if I'm not wrong, and that's it. So this is the equation. So I know during the exam you will be able to look up the formulas, so you don't have to remember things by heart, okay? And but still, if you these are not that many formulas, and if you really learn, like you understand this formula, it will be almost automatic that you know them almost by heart, okay? You can maybe not be sure of something, but and I'm not talking about this for a generic point, but this for the center of mass. So I expected this equation that you must know this equation. Also, this equation you should know, and once you know, and also this is very useful. So and once you know this, if you know this one, this equation is like it's very easy to derive from this one. And at this point, you have also this one because this basically is the and because also this one you will apply a lot of times, so it's very useful for you if you remember, like when you do exercises, this is very common, this formula, okay? So you don't have to remember this by heart, but if you really exercise you will know by heart these formulas more or less, okay? um, okay, so now let's go to specific topic, important topic of the dynamics of rigid body. Maybe I go to a new page. Okay, so let's see the case of rotating shafts. So rotating shafts, and let's see first the ideal case. So in an ideal case, we can have, let's see, we have like, this is our shaft. Oh, yeah, it would have been nice. Maybe okay. And we have, so basically we have a cylinder, let's say, which is rotating. This is the center of mass of the cylinder is here and is rotating around this axis, okay? So we have, okay, sorry, repeat. Let's consider, yeah, this body. This is, yeah, it's, you can think about a disc whose axis is this one. This is the axis of the disc. And a cylinder, which is the same thing practically. And this cylinder is attached to this shaft, which is supported in 2 points. So here we have FA and FB. And this has angular, this is a constant angular velocity omega, which is constant. And let's draw like reference frame, x, y reference frame, okay? So in the ideal case, we have various features. So first thing is that the center of mass is on the axis of rotation. Then we have another important point that okay, let's say, yeah, the axis is rigid, but we consider rigid bodies, so this is like we always have everything rigid for us, like everything we consider so far was always rigid. The axis is rigid, and very important is that we have that pi s, so the angular momentum, is parallel to the angular velocity, okay? And this actually means that this motion can be reduced, in most of cases, can be reduced to a planar motion. Okay, so now let's see, this is L1 and this is L2. So what we have here, if we have a system like this, we want to find the equation of motion and find the forces and everything of this system. So we have acceleration of the center of mass, since it's on the axis of rotation, is 0. Okay, this is something that like if you have a body which is rotating around an axis of rotation, this axis is fixed, is not moving. If the axis is not moving, each point on the axis of rotation has 0 acceleration, okay, because it's not moving. 0 velocity all the time, it means 0 acceleration. I saw sometimes done this mistake, that the velocity of a point, acceleration of a point on the axis of rotation is different from 0. Please don't make this mistake, okay? Okay, so if this acceleration is 0, we write like we have that MAS is also 0. And this means that we have that the sum of the forces must be 0, because we have that that F is equal to MA, okay? Then we have that omega is constant. Omega is constant, therefore we have that epsilon is equal to 0, okay? Then when we have that omega, so we have that, let's say we have that ds is equal to pi to theta s times epsilon plus omega cross product pi s, okay? And now we have that the epsilon is 0, so we have that this is 0, and also this is equal to 0, because omega is parallel to pi s, okay? So the cross product must be 0, okay? So this is equal to 0, okay? And this means that the moment, the sum of all the moments, and with respect to point S, must be 0, okay? So now you see the sum of all the forces is 0, sum of all the moments is 0. This is something that you learn in a course of static, okay? This is the static equilibrium equations, practically. So here you can use static equilibrium equations. So this is a very convenient case, and ideally it should be like this, but we know in engineering is not like this. In engineering we will never have that S is exactly on the axis of rotation, that it is exactly aligned, the axis, the principal axis of the disk is exactly aligned with the axis of rotation. This is something that is only ideal. In reality we don't have anything like that. So let's see what happens if this condition is not verified, okay? Now let's consider the case of a statically unbalanced shaft. So statically unbalanced shaft, it means that we have, let's draw like the same cylinder that we had before. And we have, here is the center of mass, okay? But now we have that the axis does not pass through, oh, the axis does not pass through the center of mass, okay? So we have here we have our supports, and here we have let's say here we have FAY. So a reference frame is as before, X, Y, Z is going out of the blackboard of the page, and here we have FAY and we have FAZ. Here we have FBY and we have also FBZ. Okay, you know what I mean with FBZ. So the force here in the Z direction, and we have here the that omega is equal to constant. Okay, so yeah, here is the center of mass. This is the what we call the eccentricity E, and the mass of this disk is m. Okay, so basically when we call the system shaft statically unbalanced, we call it if the center of mass is not on the axis of rotation. Okay, so the center of mass is not on the axis of rotation. Okay, so now let's write the equation of motion of this. So we have first sorry, one thing, yeah, I said E is the eccentricity, and eccentricity is something that we always have in engineering. Okay, in real system we do have an eccentricity, we cannot, is unavoidable. Okay, and acceleration of the center of mass in case of omega constant, acceleration of S is equal to 0, because in the x direction, in the x direction 0, in the y direction, so we have the we have the normal acceleration, we have minus e omega squared. Okay, I don't want to explain why we have this. If you don't know this, then you have really to repeat the beginning of the course. And in the z direction we have 0, because you have no this will not be 0 if omega was not constant. Then the acceleration in the z direction would not be 0. Okay, so this is AS. Now let's apply basic law of dynamics. I dot is equal to F. So here we have in the x direction, and let's neglect G. Okay, G is neglected because we don't want to focus here on what is the effect of the acceleration of gravity. Just let's see the fact that it's unbalanced. Okay, so here we have that 0 is equal to 0 because 0 acceleration in the x direction, 0 forces in the x direction. In the y direction we have an acceleration, so here we have minus m e omega squared is equal to, now we have two forces here, we have FAY plus FBY. Okay, and the z direction we have 0 equal to FAZ plus FBZ. Okay, now, so this is with respect to acceleration of the center of mass. So let's see the angular acceleration. So epsilon is equal to 0, and also we have that pi s. No, only one. Pi s is parallel to omega. Okay, because the principal, this is a principal direction of the. So still, the x is still the principal direction of this disk, of the cylinder. So we'll have that when we compute pi s, we will have that pi s pi s is equal to theta s times omega, and since pi s as this shape like this, so we have a theta s x 0 0 0, theta s y 0 0 0, and here we have theta s z. Because of these two zero and these two zeros, we have that pi s is parallel to omega, okay? Because omega is this, is like omega x 0 0, okay? But we have, if we compute the derivative of pi s, we have that pi s dot is equal, pi s dot, which is equal to ms. We have that pi s dot is equal to theta s I think I have to remove this because I'm going crazy. Theta s times epsilon plus omega cross product theta s times omega, and this is equal to ms. Okay, now we have this is equal to 0 because we have epsilon is 0. Then we have that this is parallel to this, so we have that this is also 0 because we have that omega is parallel to pi s. So now if you write the equation with this, with respect to the moment, so if you write basically this ds equal to ms, this is the same thing than this thing, okay? We have in the x direction we have 0 equal to 0, in the y direction we have 0, so on the left side we have all zeros because this is 0, while on the right side we have the moment. So here we have this is equal to f a z times L1 minus fbz times L2. Sorry, I forgot to call this, like this is L1 and this is L2, okay? So if you see, the force in the z direction is giving a moment with respect to y, in the respect to x, to the x-axis, we don't have any, all the forces are not giving moment because they are applied exactly on this so they're applied on this axis and they on the same line of point S. So with respect to point S, fay, faz, they don't give any moment, but with respect to wait, yes. So okay, I will pause it 1 second and think one thing. Okay. Oh. It was a good idea to pause because here there is a mistake. This is not 0 because this for faz and fbz, they have a moment with respect to point S in the x direction. So this is actually should be faz times E plus fbz times E, okay? And then we go in the z direction. This is the most interesting we have because you have 0 equal to fby times L2 minus fay times L1, okay? And now if you see this equation and all this equation, you will find out that faz is equal to fbz is equal to 0, but we have that fay is different from 0 and by, so fay and fby is also different from 0. Okay, and it depends on this. So the sum of this is given this acceleration. Okay, so even if you have L1, if you have L1 equal to L2, you will have that fay is equal to fby, but the sum of them is given by this force, okay, by minus me omega square. So it depends on the acceleration, on the mass, and on the angular velocity at the power of 2. And since what is important here is that if you see this system now, we have these forces in the y direction are different from 0, but I think that this guy is rotating even without, I'm not talking about the weight, so it's not, we don't have gravity, okay, so these are not, it's not compensating some static force, it's a dynamic force, and this is rotating. And that's all the time, whatever is the direction, we have a force of the hinge here of the support, which has to compensate this basically this eccentricity. Okay, so with the direction of the eccentricity, we will have two forces, two radial forces here on this support. And since this is rotating, this force are also rotating. So imagine you have this thing, and you have a force which is rotating, and so it's a force which changes with time, and this will cause vibration, and it can cause even very heavy vibrations. Okay, so it is really an engineering problem, like problem common in engineering. This it will also, because this eccentricity is unavoidable, we cannot do anything, it will be there, some eccentricity, we should make it as small as possible. Okay, so let's write simply that since the forces at the support at the hinge, okay, at the hinges varying rotates with the system, they generate vibrations. Okay, and this is a serious engineering problem. Engineering. Okay, so in really many cases, if you have a motor which is causing and is vibrating a lot, most of cases this is the reason. Okay, now let's put some number to have an idea of what is the meaning of this. So let's put some numbers. Okay, so let's think about a disc which has a mass of 10 kilograms. Okay, 10 kilograms is really a small mass, it's not much. Okay, and we have an eccentricity which is equal to 0.1 millimeters. Okay, it's not much. 0.1 millimeter is something very small. And imagine we have this on fan, like fan to cool down in summer. We'll have that let's say in a fan we can have and so rotation which is, let's say, 300 round per minute. Okay, and this means that we have omega is equal to 300 times 2 pi divided by 60. And if you do the calculation, we have that E times m times E times omega squared is almost equal to 1 Newton. Okay, 1 Newton is nothing because we have the static weight of this is 10 kilograms. 1 Newton is 0.1 kilograms in static sense, in terms of weight. If it's generated by weight, it's generated by a mass of 0.1 kilograms, let's say. And So this is really not a problem because the support can keep 10 kilograms, 10.1 kilograms it should keep. Okay, no problem. Let's see if we have a car engine, or we can have easily around like n, which is equal to 3000 round per minute. Same value of the mass, same eccentricity, so eccentricity is still very small, and the mass also 10 kilograms is not a big mass. Here we have m times e times omega squared is almost equal to 100 newton. Okay, so you see omega squared, so if we are increasing omega 10 times, the force will increase 100 times. Now 100 newton is correspond to 10 kilograms. Okay, so we have that now we are basically doubly, like we have a weight like the same force equal to the weight, which in general is not a big deal, but this force is rotating. So if you have a small oscillation, it will cause vibrations, and this you will see next semester in the vibration class, that vibrations can be an issue depending on the natural frequency. We are on the frequency to which is generated, but this is another topic, so you will have time to study this. And now let's see the case of an ultracentrifuge, so something going very far, rotating very fast. So ultra centrifuge, we have n can be of the order of 30,000, and in this case we have m times e times omega squared, which is close to 10,000 newton. Okay, so if you see, if you increase the spin, the angular velocity, you will really can get very high force generated by this very small eccentricity. So if you have an ultracentrifuge, you can understand that for an ultracentrifuge how is important to have no eccentricity. Even the smallest eccentricity can cause a big problem. Okay, but there is a solution to this. So since it's a big problem, many people thought about solutions to solve it, and solution is to put a mass to balance the system. Add a mass, let's say, add a mass to balance. Okay, so we have let's consider our system. We have so this is our system. We have here is the center of mass, this is the eccentricity, and here on the other side we put a mass that we call this m0. Okay, and we have we have this distance we call r, and then we'll have that in order to be balanced the system, we must have that m times e times omega squared. So this is yeah, if you do the computation again and just sum up this mass, you will obtain the same formula, just same effect, just with the mass. So okay, all these forces generated by the velocity, the acceleration of the center of mass. So if you have an acceleration of the concentrated mass which is opposite to the center of mass, you have the same effect, just with opposite signs. So you must have that m times e times omega squared must be equal to m0 times r times omega squared. Okay, so omega squared can disappear, so basically we obtain that m0 must be equal to m times e times r. Okay, and this way, if you apply this, we add mass using this formula, we will be able to compensate this effect and eliminate this force. And this is something which is done, for example, in cars. So if you have if you see like a wheel of a car, you will have so you have the here we have the tire. So yeah, this is the tire, and you will see that you have some small masses. You can have places somewhere on the I don't know how it's called. This part, this is made of steel, I guess, and on it you have some. You can have one small mass which was placed there in order to center the wheel because it was not perfect. So it was produced, but during the production they can make mistakes. It's not perfect, and you can balance it, adding some small masses. Okay, making the centering of the wheel. Let's say. Okay, so this about the static. This is called static unbalanced shaft, and even though the problem is not a static problem, is a problem is dynamic problem, because the problem is when this is rotating, still it's called statically unbalanced. Okay, because it's yeah, that's I think because it's related to the position of the center of mass. Actually, if you have gravity, this will make the center of mass go down, so it will make the wheel not to have a specific stable position, so it will be like a pendulum. I don't know. So if you think about this body hinged here, the center of mass here, this will tend to go down with the gravity. If it's not spinning, it will just stay downwards. So the center of mass will be just under the axis of rotation. Okay. So that's why it's called statically. It's arguable if statically is a good name, but that's the name which is given to it. Now let's see the case of dynamically unbalanced shaft. Okay, so and this is for the eccentricity is equal to 0. We have no eccentricity. Okay, now so let's see, we have our cylinder now that now is a little bit tilted. Okay, now I make it very tilted, but of course you usually don't have something that tilted. Oh wow, this is, oh, I cannot make I know if you see this I look stupid, but looks it's very strange to make a straight line in that way. Sorry. Now I managed to do it, and this is the axis, and here we have the center of mass. S is here, so you see S is on the axis. Okay, we have no eccentricity. I mean, we made the assumption that there is no eccentricity, and we have now these are the axis X, and here we have the axis oh, okay, this I think I will do this way to do something more reasonable. So this is Y axis, and we have acceleration, angular acceleration, like this, which is omega, which is constant. Okay, okay, so what is the peculiarity of this system? The peculiarity is that the axis of rotation is not parallel to any of the principal axis of inertia of the system. Okay, so if you see this cylinder, principal axis of inertia is one is in this disc, this the axis. So this is the axis. So the cylinder is axial symmetric around this axis. Okay, so you have this is the principal axis of inertia, and then any direction like orthogonal to this one can be principal axis of inertia, because we have this axial symmetry properties. But for sure, x is not an axis of symmetry if you have this configuration. Okay, so yeah, let's write this down. So the main property of the dynamically unbalanced shaft is that the axis of rotation is not parallel to any of the principal axes of inertia. okay, and we call the angle phi, which is this angle phi, is the angular error, okay. Okay, so what means if you have a configuration like this, like a system like this? So if you think about the matrix mass matrix of inertia with respect to center of mass in the x, y, z reference frame. Now you will understand why I write x, y, z reference frame. We'll have theta sx, and here we have all generic term with minus dxy, minus dxz, minus dxy, theta sy, minus dyz, this theta sy. Here we have minus dz minus dyz, and here we have theta sz, okay. And we have that omega is equal to omega x 0 0, okay. And this means that we have that pi s in the x, y, z reference frame. This is equal to theta s times omega, okay. And if you make this product, you obtain omega x times theta sx. Then you have this minus dxy times omega x and minus dxz times omega x, okay. So now you see that the fact that this is not zero in general, this is not zero, makes that omega is not parallel with pi s, okay, which is a property which we had before in a simplest case. Here or even in the ideal case, we have that omega is parallel to pi s, to the angular momentum, okay. And also in this case, statical unbalanced shaft, we still have that omega is parallel to the angular momentum. Now if you have a dynamically unbalanced shaft, this is not verified anymore, and this is the main thing, that this is related to the fact that the axis of rotation is not parallel to any of the principal axes of inertia. And actually this is we can say dynamic unbalanced if then is verified that pi s is not parallel with omega s, okay. This is the main thing, the important thing that is causing the system to be dynamically unbalanced. Let's see what are the consequences. So first thing, to write this matrix is a mess. If you have this, you want to write this matrix in the x, y, z coordinate reference frame, you go crazy, okay. You have to compute all the integrals. It's quite demanding. So let's work in another reference frame. Let's work in psi eta zeta reference frame. And we have that this will be psi, and this will be our eta, okay, while zeta and z are parallel. Okay, so so now we can write theta s quite comfortably, let's say, because now we are on the principal axis of inertia now. So we have the theta s will be given by theta s psi. Sorry. Okay, theta s psi. Then here we have 0 0 0. Then we have theta s eta 0, 0, 0, and theta s zeta. Okay. Okay, so we have then let's write omega s in the psi eta zeta reference frame. Now maybe it is useful to draw this. So this will be omega, this is omega, and we have this direction. This is our psi, and this is instead this is eta, while this angle is angle phi. So this means that we have in the psi direction we have omega times cosine of phi, yeah, omega times cosine of phi. Yeah, in the eta direction we have minus omega x times sine of phi, and then 0 in the zeta direction. So from this we can compute pi s in the psi eta zeta reference frame, which is given by theta s by times omega s. So it's theta s times omega s, and this will provide us theta s psi. Okay, sorry, this let me correct this. This is a psi. Okay, same thing. I no need to correct it. So yeah, theta s times omega s will have theta s psi times omega x cosine phi. Then here we have this times this, so we have minus theta s eta times omega x times sine of phi, and then 0. Okay, and we call this pi s psi, pi s eta, and 0. Okay, now we see, you see from here, you see immediately that pi s is not parallel to omega. Okay, because omega is only wait. So pi s in general is not pi. It can be parallel only if so in general it's not parallel. They are parallel if theta s psi is equal to theta s eta. In that case it would be parallel, but in general is not parallel. Okay, so let's write here pi s is not parallel to omega except if theta psi is equal to theta s psi is equal to theta s eta. Okay, what are the consequences that this pi s is not equal, so the angular momentum is not parallel to the angular velocity? So let's go back to the x, y, z coordinate reference frame. So we'll have here we have x, here we have y, then here we have psi, and here we have eta. So x, y, psi, and eta, and let's say that this is pi psi, and this is pi eta. Okay, now we have, if we project this on the xy reference frame, so in the x, y, z, we obtain we have pi okay, this should be pi s, sorry, this should be pi s psi, pi s eta. Okay, so here we have projecting these two on the x, y coordinate system. here we have pi s psi times cosine of phi. Yeah, this cosine of phi, this angle is phi, minus pi s eta times sine of phi. Then we have pi s psi times sine of phi plus, so yeah, this projected here, plus pi s eta times cosine of phi, and then 0, okay? And this is equal to pi sx pi sy 0, okay? Now if this is 0, then pi s is parallel to omega, and this but in general it is not, because this occur only if theta s psi is equal to theta s eta, okay? So this is really a special case. And now let's try to write the equation of motion for this case. We have now we have ds is equal to pi s dot. Pi s dot is equal to, so we have theta s times epsilon, which is 0, okay? Epsilon is 0 because we have omega is constant, plus omega cross product pi s, okay? And this will give us, so we have omega x 0 0 cross product pi sx pi sy and 0. And if you do this cross product, we obtain 0 0 and then omega x times pi sy, okay? We have ds is equal to ms, okay? So we have this is ds. So this means that in order to have omega constant, we need to have a moment which is not 0, okay? So okay, I repeat this because maybe you lost yourself with all the passages. So let's start again for the dynamically unbalanced shaft. The case of statically unbalanced is much easier. So let's consider a case. We have our cylinder, which is a little bit tilted with an angle phi, okay? And now we have the principal axis of inertia of this of the cylinder are not, no one of them is coincident with is parallel to the axis of rotation. We have an angle phi between the principal axis of the cylinder and the axis of rotation, which is called angular error, okay? So now if you compute the matrix theta, so the matrix moment of inertia of this, we have a full matrix, we don't have zeros. And if we compute then pi s, we have that pi s is not parallel with omega, okay, in general. And this is and this can be an issue because I mean, I will show now what I want to show why this is an issue. So to see why this is an issue, let's work in psi eta zeta coordinate because it's much easier to compute theta. So we compute theta in the psi eta zeta coordinates reference frame, and we'll have a diagonal matrix moment of inertia. Let's write omega s in the psi eta zeta reference frame. So we project omega on psi and eta, and we obtain this vector. This is the same vector. It's still omega s, which is it's just the only difference is that now we are considering it with respect to another reference frame. It's not xyz. Omega in the xyz is like this. In the psi eta zeta is like this, okay? Let's compute pi s in the psi eta zeta, theta s times omega s. If we compute this, we see that we have two terms which are not 0 here, okay? And so as I mentioned, again, this pi s is not parallel to omega. And now let's see what does imply. So let's go on with the computation. Let's go back to the xyz the reference frame now with pi s, which is easy to transform. So pi s, we have pi s psi, pi s eta. We transform that in the xy reference frame and we obtain this is just a projection. So we have just some sine cosine terms which appear, but the important thing is that this and these are different from zero. And now if you compute ds, so if you want to write this equation ds equal to ms, we have that ds is given by pi s dot. Pi s dot is given by this term, which is 0 because epsilon is 0, but this term is not 0. This term is different from 0, and this means that if we want to have something such that epsilon is 0, we need to give a moment, okay? So yeah, we need to give a torque. So in order to have ms, sorry, to have omega constant, it is needed to give a torque. In the z direction. The torque, which is ms 0 0 omega x times pi sy, okay? So this means that in general, if you have a system like this, like the ideal case, this is rotating with constant angular velocity. You have, as you assume you have no friction, you have to give no torque, or only maybe you have some friction, you give a torque in the x direction to compensate the loss given by friction, okay? In the y and the z direction, you have no forces, nothing to worry about, okay? But if this is tilted a bit, we saw that it is generating, sorry I went so fast, but we see it's generating a torque in the z direction, which should be compensated in order to keep omega constant, okay? And this also, this force is, this system is rotating, so z is orthogonal to respect to y, so we have a force which is like a torque which is rotating. This torque will be probably will be provided by the support. It means that we have also, in this case, we have a force on the support, which a force which is a torque which is generated by the by the support, okay? So so here still we have rotating forces on the support. It means that we also, in this case, we have vibrations which are generated, okay? And this is, again, this is an issue, okay? Since the system rotates, also this torque, in some sense we can say that oh, why this torque also rotates. Now this I don't understand why I put two lines. It's making this pi. Okay, also this torque rotates, and this generating vibrations, okay? So still there is a solution also in this case to avoid this problem, and what we have to do is to make this pi sy 0, okay? So let's say solution to avoid this torque is to make pi sy equal to 0, okay? If we do this, then we eliminate this term and we are fine. We have a balanced system, dynamically balanced system. So let's consider the case of let's consider this case. So we have our shaft here, and we have our oh, maybe I have to tilt the board to make it. No, wait. I feel really stupid that I cannot make a tilted line, but okay. Yeah, if I have the reference in front of me, I'm unable to draw this tilted line. So strange. And okay, so we have our system. We want to compensate this. We can put some masses as we did before. Now we have to put two, not one mass, but at least two masses, because we have we don't want to move the center of mass. The center of mass is in the correct position. We want to somehow rotate the principal axis. Okay, principal axis is like this. You want to rotate and make it go in this direction. Okay, so we'll have this mass m0 added here, and here we have another mass m0. Okay, let's call this h, and here the radius of the disk, let's call it capital with a capital R. Okay, now let's consider so we have okay, this is our direction xi. We have so let's say this is the yeah, this is the first mass. We have R, yeah, let's call this point 0 1, and no, okay, the position vector of the first mass are 0 1 in the psi eta zeta reference frame is equal to h over 2 r and 0. Okay, because this is the position vector of this mass m0 with respect to the center. But sorry, I was just copying the notes, but I don't. Let's call this point m1. So this will be our SM1. Okay, and so let's write now the moment of inertia, matrix moment of inertia. So we have theta s of the cylinder. This is not understandable. Of the cylinder in the psi eta zeta reference frame, this is equal to, so we have 1 over 2 m r squared. So now this I'm just writing the formulas. You can check, you have tables everywhere like matrix moment of inertia. On Wikipedia you will find for all the simplest geometries. Like a cylinder is geometry that you must know because you will encounter many times. Anyway, you know, like you, even if you don't remember, it's good. Just you need to know how to read it from the table. Okay, so these are the principal axes, x eta zeta, xi eta zeta. So we have 1 over 2 m r 0 r squared, then we have 0 0, here we have 0, here we have 1 over 4 m r squared plus 1 over 12 mh squared, then 0, then we have 0 0, and here we have 1 over 4 m r squared plus m plus 1 over 12 mh squared. Okay, so this is the matrix moment of inertia of the cylinder. Then we have theta s of the two masses, so 2m0, again the psi eta zeta reference frame, and this will be, so here we have r squared. So no, sorry, we have 2m0, which multiplies r squared. Here we have minus rh divided by 2. Then we have 0 minus r h divided by 2. Here we have h squared divided by 4, 0, 0, 0. And here we have h squared divided by 4 plus r squared. So this you can obtain from this vector, the position vector, and you can check. So basically, from the position vector and applying the parallel axis theorem, you can have this matrix. So I invite you, if this is not obvious for you, check it from what we was explained I think 2 weeks ago. So, and if you have question, feel free to ask, of course. So then we have theta s total in xi eta zeta reference frame is equal to so the sum of this, so we will have basically theta xi minus d xi eta 0, then we have minus d xi eta, here we have theta eta 0, so here we have still 0, this is not disturbing this direction, so here 0, 0, and here we have theta zeta. Okay, so now there are two methods. So what do we want to do? So we because yeah, this is critical, maybe I was not clear in this. So we have this cylinder which is tilted, a little bit tilted with respect to the axis of rotation. Okay, so we have some force generated which we don't want to have. We want to go to something close to the ideal case. We don't want to have this dynamically unbalanced system. So we have two masses. These two masses will not move the center of mass, which is still there. So we don't want to cause any static unbalance the system. But we want these two masses, we place there those two masses, and we want to make the system such that theta s so that this direction will be the principal direction of the system. In order not to have this, we want to make this theta sy0. Okay, so this theta sy0 means that okay, yeah, we have this, yeah, theta sy is given by this. So okay, you can go back to check everything, but important thing is that we have this phi. Okay, if this phi is different from 0, we'll have something. We want to compensate that with these two masses. Sorry, I think sometimes I'm losing myself in the explanation, and but I try to keep track. Okay, again, ask if you have questions, just ask. Okay, so there are two methods to find the correct values of m0. One method is the transformation of the angular velocity. So we want to find, let's write we want to find the correct value of m0 such that the system will be dynamically balanced. Okay, first method is transformation of the angular velocity. Okay, so what that this means, we have we transform the angular velocity. It's similar basically what we did so far. So we have omega psi eta zeta, we transform it to the coordinate. So we transform omega from the x, y, z coordinate reference frame to this psi eta zeta, and we obtain following what we had before, omega times cosine phi, then we have minus omega times sine of phi and 0, and we call this omega xi, omega eta and 0, okay? Okay, so from this we can compute pi s in the xi eta zeta reference frame. So this is equal to theta s total times omega, and this gives so if you see theta that we had before, this is the theta that we have, this is the omega, we obtain theta xi times omega times cosine of phi plus d psi eta times omega times sine of phi. Then here we have minus d psi eta times omega times cosine of phi minus theta eta omega times sine of phi, and then 0, okay? And now we know that before, if you check what we had before, here we have the, no, maybe, no, I don't want to show it in this way, just here you see this theta xi, theta eta are in any case different from 0, but these terms out of the diagonal are generated by these masses, these additional masses, okay? So adding these additional masses, we are adding this and this term, and we are also modifying this theta xi and theta eta. But what is more important, we are adding this and this, okay? And this will be then, we call this pi s xi, pi s eta and 0, okay? Now we have this pi s. We want to write pi s in the x, y, z coordinate frame, similarly to what we did before. So we'll have pi s xi times cosine of phi minus pi s eta times sine of phi. Then here we have pi s xi times sine of phi plus pi s eta times cosine of phi, and then 0, okay? Now our objective is to make this guy equal to 0, okay? So we have that this must be 0 in order to have the system dynamically balanced, okay? So if you write explicitly this term, you follow what we had here and what is the meaning of this d psi eta, this theta eta and theta psi and d psi eta here. So you write again everything, you will obtain quite a long expression, which now I'm directly writing. So we have 1 over 2 times m times r squared plus 2 m0 r squared, sorry, times omega times cosine of phi, and we have that this is, so we are taking this term and we are imposing this term equal to 0, okay? So this term we have theta s xi. Theta s xi is this, which is this. So you have theta xi. So pi s xi is this guy. Theta xi is equal to this times omega times cosine of phi. Then we'll have plus d psi eta, which is 2 m0 times r pi times rh divided by 2 times omega sine of phi times omega times sine of phi, and then here times sine of phi plus yeah, times yeah, this, why this is sine of phi, because this sine of phi is this sine of phi plus pi s eta. Pi s theta is this guy, so we have plus, then here I have minus 2 m0 r h divided by 2 omega times cosine of phi, and this is this, so all this is this term. Then I have plus minus this, so theta eta is equal to 1 over 4 m r squared plus 1 over 12 times m times h squared plus 2 m0 times h squared divided by 4 times omega sine of phi. So times omega times sine of phi, and this times cosine of phi, okay? Cosine of phi, and this must be equal to 0, okay? Now, if you solve this, we have to solve this equation with respect to m0. Solve equation with respect to m0, and usually phi is small, therefore you can assume that cosine of phi is almost equal to 1 and sine of phi is almost equal to phi, okay? Usually you can make this assumption. Anyway, the solution from this that you obtain is that m0 must be equal to m times 3r squared minus h squared times sine of 2 phi divided by 24 rh times cosine of 2 phi plus 6, which multiplies h squared minus 4r squared times sine of 2 phi, okay? So of course you don't need to remember this equation, but you should remember the procedure, okay? How to do this and what is important. So especially theoretical aspect, this is important for you to know why it's important to put these two masses, okay? So this is really something that I can ask you, why you put these two masses, and this must be clear, okay? And why on two masses and not one, while instead in the static unbalanced case, here is enough to put one mass and we don't need two, okay? Let's go back to where we were, and now you also notice one thing, that if you have the case that 3r squared minus h squared is equal to 0, then there is no need for balancing, because the system, even if it's tilted, the cylinder is still balanced, okay? So there's no need for balancing, even if it is tilted. And by the way, the fact that this unbalanced thing is sometimes even used for a positive purpose. For example, like if you want something to vibrate, and think about your phone, your cell phone, you have the vibration mode. How you can make the telephone vibrate? It's pretty simple. You take a small cylinder Okay, maybe yeah, I draw again. So you take a small cylinder, and then you make a cut in the cylinder. Okay, then you make a cut here, like something like this, and then you will have okay, maybe cylinder is much smaller cylinder, and yeah, no, yeah, okay, so let's, oh, yeah. So you have your system, like you have a small cylinder, and if you see the section, it will be something like this. So it's a circle cut somewhere, and then in this way you have the center of mass is not anymore on the axis of rotation, and this will cause a static imbalance to the cylinder. And if you just make this rotate, it will vibrate a little bit, okay? And this is the way you can have the vibration in your phone. It works in a pretty similar way, I think. I never opened a phone actually to check, but maybe you can. If you have an old phone, you can check it if you want. Okay, so I mentioned that this is one method to this is the first method to compute the values of M0, and then let's discuss the second method for computing M0 and the transformation of theta s. Transformation of theta s. So we don't go through the vectors to the angular velocity, we directly transform theta s. Now, we know that yeah, sorry, I lost a bit in the notes. Okay, so we know that this equation. Okay, now you must have learned because we used hundreds of time only today. Ps is equal to theta s times omega, and we can have a matrix T, tensor T, which brings the system from one coordinate to the other one. Okay, so we have the T brings vectors. Let's say not brings, but project. Brings is really not a good term. Project vectors from x, y, z to psi, eta, and zeta. Okay, and so if you have a vector, I have vector v, generic vector in the psi in the sorry, in the x, y, z reference frame. I will have that omega that this vector v in the psi, eta, zeta reference frame is equal to t times v in the x, y, z reference frame. Okay, and I also have that v in the x, y, z is equal to t the minus 1, so inverse of t times v in the psi, eta, zeta. Okay, so this is something that t depends, of course, on the rotation, the relative rotation between the two reference frame, and we always can define such a matrix T. Okay, I'm not sure if you studied this in geometry or in other subject, but it's something that you can always do if you have so the difference between these two systems is the reference frame is simply a rotation, so you can do relatively easily. Now let's think that we have our equation. We have that theta s in the psi, eta, zeta reference frame times omega in the xi eta zeta zeta reference frame is equal to pi s also in the psi eta zeta reference frame. Okay, now we write this omega of psi eta zeta is equal to t times omega in the x, y, z coordinate frame. Okay, so we'll have that theta s, the psi eta zeta times t times omega in the x, y, z is equal to t times pi s in the x, y, z. Okay, so we apply this transformation also that pi s in the psi eta zeta is equal to t times pi s in the x, y, z. Okay, and now let's multiply this equation by inverse of t, and let's multiply this by that, and we obtain that t to the power of minus 1 times theta s in the psi eta zeta times t times omega in the x, y, z is coordinate system is equal to pi s in the x, y, z, because here you have t to the power of minus 1 times t, okay, which is the identity matrix, and we can eliminate it. So since we have this, we have and we also have that this is analogous to writing, we also know that theta s in the x, y, z times omega in the x, y, z is equal to pi s in the x, y, z reference frame. We have that this basically is theta s in the x, y, z. Okay, so what we obtain that theta s in the x, y, z is equal to t to the power of minus 1 times theta s in the psi eta zeta times t. Okay, and with this transformation matrix we can project the matrix moment of inertia from the psi eta zeta coordinate frame to the x, y, z, which is convenient, because in this case, if you have our system with this system, we just project in the x, y, z, and we want to have that the x-axis is a principal axis of inertia, and that's it, and everything is done, and we know that the system is balanced. Okay, now how do we find this this matrix T? We have if we consider the system like this as we had so far, so we have x, y, and then we have psi and eta. So we have x, this is psi, this is y, and this is eta, and then we have this is the angle phi. We have versors here, we have the versor I, and here we have the versor j. Then we'll have the matrix T can be written by writing, so here we have the coordinate of the I versor, which is in psi it is cosine phi, and in y we have minus sine of phi, then 0. Here we have j versor here, so we have sine of phi cosine of phi and then 0. And here we have the k-versor. K-versor, so we have 0, 0, 1, okay? So practically here I'm projecting, if I have to write the coordinate of the I-versor in the psi eta coordinate frame, I would write cosine of phi, because this is cosine of phi, then projecting on eta, I have minus sine of phi. Then J, I have sine of phi, cosine of phi, and the K-versor in the Z is parallel to zeta, so I have 0, 0, 1. So in this way I can write t, I can make the inverse of t, and I can compute theta s in x, y, z coordinate from theta s in psi, eta, zeta coordinate. And I can balance the system, I can choose I can choose the additional mass such that I have the x direction will be a principal axis of inertia. Okay, so with this I finish the class, and so there are many things I think also today. I hope it was clear. If it's not clear, again I repeat for I don't know 100th time, just ask. I'm happy to answer to your question, and don't be shy to ask question. So some of you are asking question, but all the time in private chat. You can ask also on the wall of the subject, so other people who might have the same doubt will have the solution already. Okay, so don't be shy with that. If you have a problem, probably you are not the only one. Okay, and thank you for your attention, and I'll see you next week. Okay, goodbye.